So what I wanted to do was I wanted to run through kind of a little bit of a review of what's going on with the A to D converter and a revisitation of the generation of waveforms to the DAC. So this is a little bit of a continuation from our last exciting class. And what I wanted to do was kind of run through for you this basic idea that what we had done in the past was we had used a loop to read from our wavetable and then proceeded to output to the DAC. This time we're going to do the exact same thing with a difference. And the difference is we're going to specify the exact sample rate for reading from the wavetable and outputting to the DAC. In order to accomplish this, I have included the timer 1 library. And what you can do if you want to ever look for libraries is you can go under Include Library and you can click on Manage Libraries. And then if you get a little filter, your search text area, just click into there and then you can proceed to type in something like timer. And then you can see what's been installed and what hasn't been. Actually, maybe I should type in timer 1. And let me just make sure I got the name right. Oh, got to spell it out. Timer 1, and there it is. So this is a timer 1 Rev 11 installed. Here's another timer 1. I'm using this one right now, timer 1 Rev 11. I don't know much about the other one. What I did was when I proceeded to do my my setup is I said timer 1 initialize to 100 microseconds and then timer 1 attach interrupt DAC sample. And what this does is it lets me sample the DAC, sample the waveform and output it to the DAC every 100 microseconds as part of an interrupt that's triggered every 100 microseconds. I thought that was a particularly easy way in which to manipulate the timers, and that sort of handles a lot of complexity in the background about setting timer control registers, which is effectively all it does. I've looked at the code. It's quite extensive. It doesn't seem to compile at all in the Tinkercad, which is really unfortunate because I tried like crazy to get that timer 1 ported over to Tinkercad, but I just couldn't do it. Tinkercad apparently is not as faithful a simulator as we might like. So there are limits to simulators. In any case, sampling every 100 microseconds means sampling every 10, means sampling at 10 kilohertz is what it means. And then what I did was I attached this so-called DAC sample. And so in DAC sample, I started by saying, okay, I'm sampling during an interrupt. And the last thing I need is for something else to interrupt me during this sample. So I called on no interrupts, and that blocks out all the other interrupts that might occur so that I can focus on getting this sample done once every 100 microseconds. And then I proceeded to go through the sign table just like before and output it to the DAC. And here is a value which I got from my analog read over in here in the loop, and that'll update whenever it updates. I mean, that might take time. It might be in a wait mode, waiting for an analog device to read. I don't know how long it will take to do the analog. I think the default is 9.6 kilohertz. Whatever it is, I don't care because I'm going to make sure that my sampling for the audio occurs on time without interrupt every 100 microseconds. So this is kind of the real-time approach to programming, which is basically not covered at all in any other programming course that you might have in the, might take from campus as far as I know, with the possible exception of Digital Design 2, where they teach VHDL. So this is a fairly time-sensitive thing. And what we really want to do is we want to specify exactly how fast our DAC will sample. And in fact, when we get to the point of doing signal processing where we're taking a sample of data coming in from an A to D converter and then outputting a sample to the DAC, That's the kind of thing you might like to do all at once so that you can have uniform sampling on input and output. Because the last thing you want to do is have a DAC that samples at a different rate from your A to D converter if you're in the middle of some kind of a process that requires real-time input. So it's really good to know things like, I'm going to run at a sample rate of exactly 10 kilohertz. That has implications in terms of your frequency response, right? Because what happens is you have to think in terms of the sample rate of the DAC being twice the highest fundamental frequency you can possibly detect. And reason why is because of the Nyquist theorem, which says you have to sample at exactly twice the rate of the highest fundamental frequency. That includes partials, that is the harmonics of the frequency that you're interested in detecting. So that means I can't go up any higher than perhaps, well, the maximum fundamental frequency would be 5 kilohertz. I must be below 5 kilohertz when I do my synthesis, or when I do my sampling off of the wavetable, and that's important. And we need to know that, because if we know how many samples we're taking from the wavetable, we can divide that number of samples into the 10 kilohertz, and we'll be able to compute exactly what the frequency is of the periodic generator when we go to create our sine wave. In other words, if you told me I have 10,000 samples, that wouldn't be good, right? Because then if I'm sampling at 10 kilohertz, I'm basically outputting one full period every second or something. It just doesn't make sense, right? So you have to figure out N. In our case, I think it was 128. If you sampled every one of those elements, you would have to take 10 kilohertz sample rate, which is, I'm just using this calculator now, and divide by 128. And if you sampled every single sample, you'd be outputting a waveform at 78 hertz. So that's not particularly high in value, but that's the lowest frequency I could go. And then probably end up being somewhat higher, right? Because you actually want to think in terms of, you know, giving it a little headroom. So I can't go any higher than 4 kilohertz, that's for sure. Probably can't go any lower in frequency than 78 hertz, given N. And now I can proceed to try and give a demo. Let's see if this works. So you could probably hear that now. And then I'll just sort of sweep the
What are you changing with the sweep?
I'm changing the variable resistor on the analog shield, the DSP shield. So that would be what analog read is reading in, right? And what we're doing here is we're doing a DAC sample as part of an interrupt, and we're trying to be precise about the frequency of the sampling. And so that's the goal in all of this. And after the DAC sample is done, we go and we re-enable the interrupts. So that's kind of a key element here in our system. And what I did was I created a little bit of a demo using an oscope on an iPad. And I took that demo and I turned it into a Vimeo, and then I took the Vimeo and I posted it up to the microprocessors page. And now I think maybe you can find the iPad oscope here. Let's see if that works. Now, why does it come out sideways? I don't understand that at all. Isn't that bizarre? It was not sideways when I recorded it. It was frontways. So there, that highest frequency, which you could see right up in here, that's 4,998 hertz. And then we're going to go down in frequency. You can see the frequencies being measured here sideways. Why is it sideways? I can't understand it. I mean, that's bizarre, right? Why would it do that? And of course, I'm coupling the speaker with the microphone on the iPad. So there's bound to be some distortion, but here you can see it looks like a really steady as a rock sine wave. You can't get that with normal oscopes. And here's the frequency as it is registered by the interpreter. So that's kind of interesting.
So why was it looking a little wiggly when in certain frequencies or certain variable resistor values?
Not sure. That's a good question. Yeah, how come it doesn't look like a pure sine wave? Well, let's think about this. We're going through a speaker. We're coming in on a microphone. It's not exactly a proper way to set up a piece of test equipment. I was sort of thinking about different ways to do this with software oscilloscopes, and I think we had an issue like that with the software oscilloscope here on lab 6. Let's take a look. So this was coming in on the Windows computer. Let's see if we can't get this to speed up a little bit.
You could probably do it in the settings of this video.
So there it is. It's not quite, even on the Windows computer here, and it's kind of loud and obnoxious.
And
turn this down.
Professor, do you remember when I was in the lab and we actually used the male-to-male audio auxiliary cable?
I do remember that. We didn't see this there,
No,
right?
no, we did. Yeah, we did.
Did we?
Yeah, even on the oscilloscope we did. But on the oscilloscope, it was more of a, it looked like a pulse or a step.
Yeah, that's right. You are going to have a pulse or a step because you're skipping around in the waveform by incrementing the index register. You're not synthesizing a sine wave at a different frequency. What you're doing is you're jumping through the wavetable of a sine wave with different jump increments. That's not the same as resynthesizing a sine wave. So it's likely you're going to get a slightly different waveform if you're jumping from one sine wave step to the other. So maybe that's an answer. I could have tried to synthesize these things in how you say real time using the trig function, but I don't think that's a good way to go for sine waves. If you want to do a real-time synthesis of a waveform, do something like a sawtooth wave. And the sawtooth wave, it's just incrementing by 1 until you get to the top, and then you drop it to 0. And then you can synthesize that without using trig functions at all, and you don't have to worry about using multiple CPU cycles to compute something like a trig function, because that stuff is double precision floating point, and there's no way your little 8-bit toaster controller is going to do that in one CPU cycle. But an increment, that's different. That it can do in one CPU cycle, not a problem. So that's a pretty easy way to go if you wanted to do something like that. Instead of outputting sine waves, you could output a sawtooth wave. And then you can get rid of all of this stuff about the sine tables and init sine. And when you do these outputs, well, really all you want is to output your index, I suppose, and then make the index equal to, well, you probably want to change the code quite a bit. Because we've set up n, I would like to say let the index go to from 0 to n, where n is perhaps 128. Yeah. So if you wanted that to go to 1,000, let's see, 4,095, 4,096, then take 4,096 divided through by 128 and get a number like 32. So if you wanted the output to be equal to index times 32, then you wouldn't need the sine table. wonder if you need times index instead of times 32. If I times, that would be times 4, times 8, times 16, times 32, right? So that's shifting index over to the left. That's going to be done in one CPU cycle. And so the shift will take precedent. The index will get shifted. Output will increment 128 times. And then, let's see, what else do I need to do? Index is resetting itself whenever it gets to n. Oh gosh, I don't know. That might work. It did it. I did it. What does that sound like? Oh, it's not working. Oh, embarrassing. Well, life in the big city. I'm not quite sure why that didn't work. That sounded like something that should have worked, right?
Wait, can we see that again?
Let's do times 32 instead, just in case I've had a brain fart. Oh, I forgot to reset the Arduino after the upload. That actually is really obnoxious. So that's that probably would have worked then had I remembered to reset the Arduino after the upload. Let's see. Let's give it a go. That's totally obnoxious.
It's running the last code, is it not?
It's running who?
The last code.
Oh, did we not upload? I thought it said done uploading.
It did, but sometimes the Arduino just doesn't accept the code and just runs the past one, I think.
No, I don't think that's true.
No? Okay. Then it must be that.
So, obnoxious waveform number 10. So there you go. So that'll get you that instead of the sine wave. And then you don't have to worry about jumping around on sine tables. You can just continuously increment your sawtooth wave. But that is not a great way to go, I think, if you don't like the way sawtooth waves. Sawtooth waveform hack. Here's my sawtooth waveform hack. So that's a analog read. That's going to do stop and wait protocol in the main loop. But we don't have to worry too much about how long that takes since we've got this DAC sample happening. Now, last time we were looking at A to D converters, and you can see I've changed the volume somewhat over in here. This is actually so loud that I was afraid I was going to blow my speakers, so I cranked it down. I used this init ADC to gain access directly to registers. And so we had reviewed what happens when we start to manipulate these ADC status registers at the bit level. And so what I wanted to do was kind of point out some nice ways in which you can set up your code to make it a little bit more readable. And so I worked kind of hard making this as readable as I could possibly make it. You can have up to 16 A to D inputs depending upon which Arduino you're at. So there's the least significant 4 bits available in the AD mux. And what you want to do is figure out which A to D you want and then mask it with the least significant 4 bits. And this sets the analog input to be 0, but you can make this 1, 2, 3, 4, or 5 as well. So that gives you 6 inputs on your Uno. And then what you want to do, sorry, I've got this phone ringing. I've got to silence it now. They only call me when I'm in class. So what you want to do is then look at your reference voltage inputs, and you can change that. And what I've done in here is I'm using the reference 0. REF0 is being set to 1, and so that says I'm going to use the VCC with an external capacitor at the analog reference pin. So that's saying he wants inputs that go from 0 to 5 volts, but I could change it to use the internal reference, which is a precision 2.56 volts. And if I did that, then I would have to say 80 mecs or equals, and then I'd have to do ref 0 and ref 1. So if I wanted the 2.4 volt version, I might do something like this. And that would be the 2.56 volt ref setting instead of the 5 volt reference setting. I mean, if you had a guitar going in and you know it was going to be like 1 volt peak to peak, this might be a little bit more appropriate than the other one. So kind of have to figure out which you're doing. The other bits for the 80 mux, there's this thing called left adjust. And you can left or right adjust your 10 bits. And so here, if you're going to left adjust your 8 of the 10 bits, and you just want those most significant 8 bits, you left adjust them. And then you can proceed to sample them just by reading ADCH and setting it equal to your high bits, your 8 bits, most significant 8 bits. And that's good if you only need 8 bits of precision, which is probably fine for our little volume indicator. Then you wouldn't need to do something like shifting things to the right twice. I don't know if you noticed this in the DAC sample, but we're always shifting to the right. But that's because we're assuming that the value is coming in as a 10-bit value, and it's being read in however long it takes to read from analog read. But instead, if you wanted to do something with precision, you can essentially say, look, I'm just going to digitize the first 8 bits. I'll shift it over, and then I'm going to grab it using ADCH, and that'll give me the high bits, the high 8 bits, and then I'll be done. Then comes the interesting thing about the prescaler. So we've got a 16 megahertz clock going into a prescaler, which essentially is a divider, and it divides down by integral powers of 2 from 2 to 128. And when you do that, you basically take a successive approximation ADD converter's conversion register, and you power it with the divided down version of the system clock. So, for example, if you had a divide by 2 on a 16 megahertz crystal, your successive approximation register is getting an 8 megahertz signal. If you know it takes you 13 cycles to do a conversion, then you take that 8 megahertz and divide by 13, and you get like this number right in through here, 0.615385 megahertz, which is not exactly right, but that's close. And then that's how many hertz it is, and if you round it up, it's 615 kilohertz sample rate. So what happens with your prescaler is you can change your sample rate. I happen to think 615 kilohertz sample rate is much, much too fast for anything I want to do with signal processing. So what I'll do is I'll use a prescaler of something like 128, just slow everything down. And what that does is it gives me a sample rate of it gives me a clock frequency for the input to the successive approximation ADD converter of 125 kilohertz. And if I take that 125 kilohertz and divide through by 13 cycles per conversion, then I get to 9.6 kilohertz which is a nice slow rate for something like the diddle pot that you plan on turning, because you're not going to turn your diddle pot at 9.6 kilohertz, almost certainly. And then what you want to do is you want to figure out how to set those bits. So here it is, bits 0, 1, and 2. I'm sorry, yeah, 0, 1, and 2 are 3 bits from left to right. And you can see they're ADPS 0, ADPS 1, and ADPS 2. And so what you do is if you said, you know, I want to set ADPS 0, right, what that does is it sets this bit and gives you a divide by 2 clock. If I want to set ADPS 1, which is there, then that gives you the divide by 4. And here's how you get your divide by 8. That's going to set both ADPS 1 and 0. There's 1 and 0. ADPS just 2, that'll give you a divide by 16. So here's just 2 by 16. And so that's a nice way to go because you're setting the bits all at once and you're doing it surgically without using the so-called SBI and CBI or set bit and clear bit invocations. And these are all being preset as constants. And then you just have to select for one and say, look, I'll go to my ADC control register and I'll just set to 128 as my divide down. And if I divide by 128 on a 16 megahertz clock, I know I'm going to go at 125 kilohertz for my sample, my successive approximation ADD converters register input, and therefore divide by 13, I'll have a 9.6 kilohertz conversion rate. And the other thing you want to do is set it up so that it auto triggers. Now that auto trigger means it's going to free run. It's going to convert as fast as it can at 9.6 kilohertz, and then it'll generate an interrupt. And now you have to worry, oh, gee, is this going to interrupt my ability to output to the DAC? And the answer is no, because during that period of time, you're going to say no interrupts. And if what that means is you lose an ADD converter input as a result, because you're in the middle of a non-interruptible service, you won't care that much because you're really just going to get it the next time around. And so what that means is it's kind of okay, since it's a manual input, that your stuff is interrupt driven and you'll be in the middle of something that can't be interrupted. So you kind of have to really be thoughtful about how you mask interrupts, because otherwise you're going to miss perhaps important events. But having a human being do a diddle pot is not that urgent an event as opposed to outputting to the DAC, which is a higher priority item. So you really have to think about why you want to have the interrupts turned off. And so then if you enable interrupts over in here, and then you enable your ADD converter, and then you say, okay, you start free running and convert whenever you can, and then generate an interrupt, what happens is you'll get an inversion of control. When the interrupt occurs, when the ADD converter is done converting, it'll call interrupt service routine, ISR, with the ADC vector. And what you're going to do is you're just going to grab the most significant 8 bits, because you've already shifted things to the left by 8 bits. You put it into your value instead of what's here in the loop, where we said something on the order of analog read. And so then what that's going to do is it'll keep that value up to date. You'll be able to use the value when you proceed to do things like set DX. And so then in theory, the only thing you have to do to switch from the manual analog read, which runs however long it runs in, to something that runs only when it's done converting, is you would comment something like this out. You probably don't need your micros, but you don't need any of that. And now you want to invoke init ADC as part of your setup, right? Because now you're setting things up to work on as an interrupt-driven ADD converter. And so This is the part of the code that I just got to this morning. I was going to test it before I started class, and I didn't quite get that far. So here we're sort of just trying things for the first time. You know what I'll do is I'll initialize this ADC before I start this timer. So we'll initialize the sign, initialize the ADC, and cross my fingers and hope this works. Let's see. So we'll upload the code and turn on the speaker. What could possibly go wrong? Let's see. And you know what happens when you're doing things where you might interrupt a waveform generation, like a nice fine sine wave like this, is you'll get a glitch. And you want to avoid those glitches. And that's why you want to control when outputs occur on the DAC and when interrupts can and cannot occur. And so this is quite nice because now you've got, let me turn this down now because it's annoying. So now you've got a nice interrupt-driven system. And look at this loop. There's nothing in here. And you can kind of do, I don't know, whatever you want to in this loop. And because everything is interrupt driven, the loop will run however fast it runs, but it won't be a priority task. So if I just said something important like, I don't know what to do. Serial.println, Mickey Mouse is my hero. You can tell I don't know what to do. So what we'll do, while Mickey Mouse is my hero, is, oh, maybe we can output here. Serial.println val. And then we'll put in a space or perhaps a colon there. And then let's see if we can get a clean sine wave, even though we have all this printing going on. Because normally that printing would interrupt a whole bunch of stuff. So this is printing at what speed? Serial begin 250 kilobits per second. That is way fast, right? It's as fast as I could envision this thing running. Let's see how it sounds. I hope it doesn't sound awful. And so we've got all these things going on in the background. A to D converters are happening, printing is happening, and it's all because we're, you know, interrupting things and we're interrupt driven. And it looks like it's multitasking, but it's really not. It's carefully dividing its attention between the high priority task, which is the output to the DAC, the lower priority task, which is read from the A to D converter, and the lowest priority task, which is output something to the serial port. Now, outputting to the serial port, you know, it says it's fast, right? 250, whatever this is, kilobits, kilobaud. But the problem is that's still really, really slow compared with a 16 megahertz computer. And in fact, if you think about it, I could probably change this to be, I don't know, something really slow, like 9600 baud. And then what? And then upload it again, I suppose. And it should still run properly in theory, I hope. Oh, he says it's done uploading. Let's go to the serial monitor and check the baud rate. 9600. It's got a match, you know. And you can see how slow it's printing. Oh my God, it's so slow. But it doesn't matter to me because everything else is running nice and fast in the background. And it doesn't matter that the serial port is doing whatever it's doing, however slow it may be. In fact, I think it sounds even better when the serial port is running slower because it's taking far less time from the Arduino to do its little printing thing. So that's a kind of multitasking. It's not really multitasking, I guess. Interrupt-driven real-time programming. That's what it is. And that's what we're doing. So the key, we did a timer attachment. We're doing sampling. If we wanted to sample at 125 microseconds, which is the same sample rate as the A to D converter, we could do that simply by typing it in there. And not to put too fine a point on it, but if I took 125 times 10 to the minus 6, and then raise that to the minus 1 power, I get a number that's 8 kilohertz. So 125. It's not quite the same as what I expected. What did we say we were going to go at? 9.6 kilohertz? So how are we getting that? That's 16 megahertz divided by 128. So that gives me a number of 125 kilohertz. 125 kilohertz divided by 13 gives me 9.6 kilohertz. 9.6 kilohertz times 10 to the 3. Oh, I got that wrong. Well, let's see. We'll do it again. 16 divided by 128 is 125 kilohertz. Divided by 13 is giving me 9.6 kilohertz. What I wanted to know was, what is the period for 9.6 kilohertz? So if I raise it to the minus 1 power, the period is 104 microseconds. That might be right. So so I need 104 microseconds. Let's see if that's true. 16,000 divided by 104 gives me no, that's not right. What is the frequency for 104 microseconds? That would be 104 microseconds is 104 times 10 to the minus 6 seconds, right? Raise that to the minus 1 power, and it gives you 9,615 hertz, which is 9.6 kilohertz. So what you really want, if you want to match the A to D converter sampling rate with the output on your DAC, is you want to go to 104 microseconds. That is 9.6 kilohertz. So now the DAC is going to match the sample rate of the A to D converter, in theory. And what does that sound like? Just out of curiosity. That's cool. So if instead of digitizing a slowly moving waveform, we wanted to digitize something that was relatively quick, like an analog input, this would be a way to do it, even though the A to D converter is running free running, because at least the inputs and outputs would be roughly equal in rate, if not synchronized. So that's the code. What do you think of that? Is it more clear now because of you know, this structure gives you all the different possible prescalers. That's what the PS is for, by the way. It stands for prescaler. And so that gives you an opportunity to essentially assign all the different features you can assign to the A to D converter, and to give it that ability to give you that 8 bits whenever it's done. enabling an interrupt. So I thought that was pretty cool. It gets you kind of deeper into the timer-based systems. So that's the new code for today. Thought you might like to see that. Now we have a homework due on Thursday next, and I think it's homework number 6. Isn't that right? You guys are a silent bunch. So I'll just bring it up. So there's your homeworks. And here is homework number 6, and that's on the ADD converter. So we kind of reviewed the ADD converter a little bit again just now. So that's cool. And if you wanted to, you could see the options on the ADD converter homework. And I think it says it's due the 15th, which is, well, today's the 12th. So that's got to be Wednesday, right? No, Thursday. Thursday, end of day. So that's good. And so you guys have an opportunity now to ask me questions about homework 6. Let's take a look at it together and see if there's anything here that we need to try to address. Actually, you know what? This is not showing me the whole homework. Let's go back. I'll do this. Let's do edit. I think that's easier. So I can see that. Let me ask, did you guys have any questions about homework, about the homework? Homework 6? No questions? So hearing no questions about homework 6, I guess I can go over homework, well, the next homework, which would be homework number 7. You sure you have no questions about homework 6? On the ADD converter?
One sec.
Well, what we'll do, let's do this. I'll pretend I'm a student and I'm just going to hit begin. So let's take a look at this. We've got this thing here called the baud rate, which is defined in a constant. And looks like we're printing out something in ASCII for a sensor value. So that's interesting. I mean, what's that about? And so sensor values are coming in, I would guess, as integers. Here they are. It's an integer for sure. And then we're sending it out as ASCII. So to send it as ASCII, we do a serial print line, and then we're telling it to do a \R. What's that mean? What's a \R? Anybody know about these things? \R is a carriage return, in case you were wondering. So in other words, what happens in various platforms as you go from Unix to the Mac to Windows is they use various different ways to terminate a new line. So you can't rely upon print line to do what you want it to do for certain devices. If what you want to do, for example, the SIR1 robots use ASCII on an RS-232 line. They want a carriage return. They want that \R in there. And if you're on a computer that only outputs a line feed or outputs a line feed and a carriage return, then it's essentially confusing the microcontroller. And so what you want to do is be explicit about what you need in order to start a new line, and that's usually device specific. Whereas when somebody says print line, it'll do the right thing for the console on that device. It'll print a new line, no doubt, but if the input is waiting to receive a proper carriage return, you want to include a proper carriage return in there. So that's what that's about. So then when you look at like the ASCII value for carriage return, it's an ASCII 13. So that's not a visible character except by virtue of the fact that it does a carriage return. Historically, the reason you want a carriage return and then a line feed is because if you have a mechanical, or let's say an electromechanical typewriter known as a teletype, it takes a long time for the carriage to return to the beginning of the line because it's physically moving a long distance, whereas advancing the platen to get another line of paper forward doesn't take much time. So you put in carriage return first and then line feed. That's where that came from. And that's why you have some computer text files being stored with both a carriage return and a line feed, or just a line feed, or just a carriage return. And the three different conventions are handled differently on three different platforms: Mac, Unix, and Windows. And that's really annoying, especially for people who are moving text files back and forth, because they lose the carriage returns as they go. Oftentimes, Notepad and WordPad are at odds with one another as a result. So when you look at something like, this prints data to the serial port as a human readable ASCII text followed by a carriage return and a new line character. Is it true or false? And the answer is false. It doesn't, the backslash R only does one thing. It creates the carriage return. So here comes another question. Let's see, send binary. So we saw the send binary thing, and now it looks like it's taking value low byte and then taking value high byte and writing it out to the serial port. And so it's doing it as I would call it numeric values, 1 byte at a time. This is how we send ASCII to the serial port. And this is how we send the numeric values out to the serial port in binary. So that's an interesting point, right? Because, well, binary is a more efficient way to do transmission over a serial line. So if we're wanting to send values as binary, breaking them up into the low and high bytes might make sense, especially if we know we only need 2 bytes. And if we do send things out in binary, we don't necessarily have to send out carriage returns each time. You can send a large binary blob out to the serial port. And that's kind of a good thing to be able to do, because sending the binary blob out to the serial port might be a good way to communicate to the host some binary data. You know that in the past, when we were doing plotting, we were always sending out a carriage return or else the plot wasn't going to work. But here we can send out binary, and perhaps it's more efficient than sending ASCII. If you send ASCII and you want the numbers, then you've got to parse every integer. We just, that is the case. So you guys tell me. Is it true or false? We use send binary because it's more efficient at binary transmission than send ASCII. Is that true?
Yes.
Yes, it is. That is true. Thank you. So here's another one, question 3. There's the analog in pin. We saw how analog read was working before. We can use interrupt-driven stuff. What's interesting about the interrupt-driven stuff is, we can interrupt the interrupt-driven stuff, or we can mask out interrupts so that they don't interrupt us. Let's see now. Is analog read generally slower than an interrupt-driven analog read?
I think the same speed.
Yeah, they can run at the same speed. You set up the analog read in free running mode, and you don't have to um, uh, rely upon this as being somewhat faster. In fact, the default rate on that is 9.6 kilohertz. It's all using the same underlying hardware that we were directly manipulating before with the bit manipulations. So it doesn't have any inherent disadvantage or advantage, but having something that's interrupt driven has an inherent advantage, because now you can have other things running in the background, like printing. So then it says there are 1,000 microseconds in a millisecond and 1,000,000 microseconds in a second. Well, what do you think of that? How many microseconds in a second?
I'm sorry, what? How many?
And how many microseconds are in a second?
1,000,000?
1,000,000, yeah. And there's 1,000 milliseconds in a second, and so there's 1,000 microseconds in a millisecond. It's 3 orders of magnitude difference from a millisecond is 3 orders of magnitude slower than a microsecond, and a microsecond is 6 orders of magnitude faster than a second. So,
True.
micros versus millis. So then there's this thing in micros which will give you the number of microseconds since the Arduino began running the current program. That's actually kind of an important thing, right? Because what that does is allows us to determine how fast something is running. That's actually important, because if you have to know how fast your DAC is sampling, you might like to measure something like that. So you might say, oh, you know what? Let's do micros, and we'll make a nice long thing called start equals micros. Okay. And then what we'll do is after the DAC write occurs is, we'll turn off this interrupt thing. We'll say long elapsed time is equal to micros minus the start. And now we can do serial dot println conversion in end quote and paren sem. Let's get rid of the ln in there. Serial dot print line elp and paren sem serial dot print line space micro seconds. All right, so there you go. Now we can know how fast the actual conversion is occurring. So you can sort of see what's happening here, right? Because we take it.
Wouldn't you want to delete the second line, print line, and print lines, or you can't?
You mean no interrupts?
No. You're. Do you want to? The reason you put a space in microseconds before the word, wasn't it so that it would just?
Oh, right. We want this all on the same line. Yes, thank you. And so we probably don't need the serial printing of Mickey Mouse as my hero anymore. And now the printing is going to occur as part of this DAC sample, but because it's outside of the interrupt screening system, we don't expect the serial print to block any of the executions. And notice the loop is completely empty here, so it's all being interrupt driven now. Now the question is, how fast is that DAC running? So let's take a look. I don't really know. I want the serial port, serial monitor, and it didn't print anything. What's going on? It said it printed start and then it printed con. Where on earth did it? Oh, it started printing conversion in. And then it stopped. Gee, that's weird. Isn't that weird? That's weird. I'm going to hit restart and see if, how about that? This is unexpected behavior. Let's put it in a loop. Let's make the ELP long a global. And that's the elapsed time. I'll set it equal to 0. What we'll do is we'll go into the interrupt service routine, and we will put this in our loop. See what happens here. I think it returned from the interrupt as soon as I
Monitor's still up on the back right there.
the monitor is up here. Oh, 8 microseconds. That's pretty good, actually.
So you just had to declare the ELP value, and then why would you put it in the loop then?
I put it in a loop so the loop could have access to it. By making it global, it went beyond the scope of the DAC sample.
Gotcha.
In fact, I could make the start a global as well. That way you don't have to locally initialize a new variable when you enter into the interrupt service routine. It's a bit of a speed hack. So we'll make the start equal to 0. I don't think that's going to change the rate at which this runs. The printing is so slow, it probably got interrupted by the A to D converter. So there we go. It's running like really fast. Now, if I wanted to, I could probably change the rate, right? So 8 microseconds, very fast. This we could probably make. Why is it running in 8 microseconds? I thought it should run a little bit slower than that. That's interesting, isn't it? 150 microseconds is the timer. Oh, he's not telling us how fast he's being invoked. He's telling us how fast he's doing the conversion. So he could indeed be invoked every 100 microseconds, and when he's invoked, the entire subroutine only takes 8 microseconds. So that's fine. That's exactly right. It's what you'd expect. Right? Because why? Writing to the DAC takes as long as it takes, but how fast you write to the DAC is different than how often you write to the DAC. So it takes you 8 microseconds to do the actual write, but you're doing it once every 100 microseconds. So every 100 microseconds, you take 8 microseconds out of your day and write out to the DAC. So that's pretty cool, actually. And the conversion is actually very consistent here. So that's good to know, and it shows you how to do the benchmarking. So that's actually quite educational. So now we have the number of microseconds since the Arduino began running. The current program on a 16 megahertz Arduino board, it has a resolution of 4 microseconds. So this is 8 microsecond conversion time plus or minus 4 microseconds. Right? So it could be 4 microseconds, it could be 12. Right? That's a substantial error when you're down to the microsecond resolution. And so that's true, actually. And it's kind of an interesting idea, right? Because if you said, well, let's see, I wonder what the frequency is for 4 microseconds. So it's 4 times 10 to the minus 6, right? Then take that number and raise it to the minus 1 power, and what do you get? And yeah, we don't get 16 million. So why we get a number that's like 250,000? That's weird. So 4 microseconds, let's see, if I have 16, let's see, 4 divided by 1, 1, 2, 3, 4, 5, 6, and then raise it to the -1 power, I get, yeah, 250,000. So that's 250 kilohertz. So this has got something to do with some other timer that's trying to give us information about elapsed time. This micros is really not as accurate as you might think. So here's another one. I like this. This is kind of interesting. I have 8 channels of ADD converter on some app megas, especially the mega. Yeah, the app mega is a little bit bigger than the Uno. They all have 10-bit resolution. If I range from 0 to 5 volts, then I would expect an ADC value to go from 0 to 123 volts, and that 2.5 volts would correspond to a number of 512. So that sort of makes sense. And now here comes the actual, the refs, right? So let's take a look at the code now and see if we can relate it to the refs. So somewhere in here we're going to find, right through here, the refs, 0, 1, 2, and 3 in binary. And so now let's see if we can get both of these things up at the same time. And so now you hear 0, 0, A ref, internal V ref is on. So let's see, internal V ref is off. They're using the external analog reference. So you can supply a separate reference to the Arduino Uno and use that. So if you said to me, I know that I'm going to be using my favorite guitar and its input is going to be exactly 0 to 1 volts, I could put in a 1 volt reference and that would be okay. And if you said to me, well, no, guitar outputs are low, it's going to be plus or minus 125 millivolts, which is probably a little bit closer to the actual output of a pickup, you could use a 250 millivolt reference externally and give it a precision reference and it'll amplify that and use that for its ADD converter. So that's kind of a nice feature. Then here comes one where you're using the analog VCC, which is 5 volts. And then we have an internal voltage reference that goes to 2.56. And you can see where the bits are. They're in bits 6 and 7. And so what we're doing over in here is we're setting the REF S0 to a 1, which means we're going to be using the VCC as our reference. So that's where that code comes from. And then comes this other thing, which is I feel like this is a lot of bit flipping kind of stuff, but here it says ADSP2 through 0 are the actual ADC inputs. So if you look at down and through here, ADPS2 through 0, you can see where these numbers 0 give us our prescaler. So let's take a look at the prescaler again. PS is for prescaler. And now we can see ADPS0 being set to a 1 is going to give us a divide by 2. And so here it is being set to a 1. And it gives us a divide by 2. In fact, if we set it to a 0, it's going to be a divide by 2 because that's the minimum we can use for our prescaler is divide by 2. So that's kind of an interesting thing. So now you've got all your divide stuff in there. So that's how we kind of started the the lecture. We said, oh, well, let's take a look at all the different possible prescalers. And then there's this ADSC thing going on. And there it is here. And that starts the conversion. Here's ADEN. This is the enable, and sure enough, we've got ADEN, and we have to enable. And that, that's bit flipping inside of this control register. Then comes ADIE, enable interrupts, and that is bit 3. And what we'll do is we'll look for ADIE, and here it is. ADC interrupt enable. When this bit is set to 1, the ADC interrupt is enabled, and this is used in the case of interrupt-driven ADCs. So when it's done, it's going to interrupt and call the interrupt service routine with the ADC vector. It'll call ISR with ADC vector, and we'll be able to grab out ADCH. Or if we're doing a 10-bit conversion, we'll get the other 2 bits from ADCL. The rest of the bits. And if you've got everything left justified, your most significant 8 bits will be in ADCH, and then the most significant 2 bits in ADCL will be the rest of the 10 bits. Because you don't get a 16-bit ADD converter here. We don't have that. So, as much as you might like, to have it, we don't have it. Unless you want to add the hardware, which is, I guess you could do that. Let's see now. What else do we need to know? So we've got the reference. We got the ADMUX analog inputs. Let's take a look at that. So this is the control register. Did we do the ADMUX? Yeah, we did that already. There's the ADMUX analog inputs. And let's see, I think that covers just about everything. Let's take a look at this code and make sure we've got it all. And here's the auto trigger, a date, auto trigger, enable. And so that's right in through here. Setting this to 1 enables auto triggering automatically every time there's a rising edge of a clock pulse. And that lets it free run. So here's a series of prescaler settings. Assuming a crystal frequency of 16 megahertz and a range of 50 to 200 kilohertz, what prescaler of 128, what will that buy us? So we take the 16 megahertz divided by 128, we get 125 kilohertz input into the successive approximation ADD converter. That's going to take us perhaps 13 cycles. So we'll divide this by 13 in order to get an actual conversion rate. And I think it came out to be 9.6 kilohertz. But ADC clock frequency is not the same thing as ADC sample. So that's different, right? So does it mean that the ADC clock frequency is 125 kilohertz? Well, we just kind of went through that, right? I mean, here's the frequency right in through here. We take the prescaler, divide it into 16 megahertz crystal, and that gives us the input into the ADD converter. So that's your 125 kilohertz right there. I'm not sure you guys are awake. You guys awake here? Anybody out there?
Hello.
Hello. Good. Good. Yeah, wake up. So, right. So if you have a prescaler of 128, take your 16 megahertz, divide by 128, and that'll give you the frequency for the ADD converter. And so that's 125 kilohertz. And that's true. You must realize that knowing that this is true is not as important as knowing why it's true. This is important, right? Because if you're going to be programming microcontrollers, you're going to have to try and figure these things out for yourself. It's not going to be a multiple choice test when you get to industry and you start programming these things. Let's try this again. So let's have a look at what we've got here. So here's our 128 prescaler, right? And we'd like to know what is the sampling period. So what do? We take our 16 megahertz, we divide through by 128, and we get a number, which is 125 kilohertz. We take our 125 kilohertz, we divide through by 13, and we get a number, and that's 9.6 kilohertz, right? So 9.6 kilohertz. You want the period on this. It's 1 divided by 9615, I think it comes to. And now you can get sort of like the period if you want. Or, you know, there are a few different ways you can do this, but I'm thinking, you know, you guys are going to want to know things like the period on your sample rate, either the frequency of sampling or the period of sampling, one or the other. They're sort of the inverse of one another. If I had 16 megahertz, another way to do this, and divided through by 128, I had 125 kilohertz. What's 1 divided by 125,000? Yeah, that's 8 times 10 to the minus 6. So that's 8 microseconds. So 16 megahertz divided by 128 gives us an 8 microsecond period on input to the Arduino successive approximation ADD converter. And if you wanted to take that 8 megahertz and multiply it by 13 cycles, that would be 104 microseconds. It's kind of long, actually. And if you took the 104 microseconds and you said, you know, 1 million divided by 104, you get 9,615 hertz, which is 9.6 kilohertz. So that's kind of how I approach that. A couple ways to do that.
Professor, how did you get 8 microseconds again?
So here's what you do. If you have 16 megahertz and you divide through by 128, that's your prescaler. That gives you a 125 kilohertz rate, right? 1 divided by 125, 1, 2, 3, should give me the period, which is 8 times 10 to the minus 6. And that's 8 microseconds.
Okay, thank you.
So that's how I do that. So then here comes this interesting bit of code. There's a serial setup, and he's giving me results of 20 microseconds. And I've got several samples from the analog read, and then several stop times. And I'd like to know, you know, if it's being consistent as I do several samples. And here I'm doing analog read, and it's giving me a 20 microsecond read time. And if you ever wanted to know, you know, how fast is that? take 1,000,000. Let's see, take 20. Let's see if I can do this. 20 times 10 to the minus 6. That should be 20 microseconds. Raise it to the minus 1 power. And that gives me 50 kilohertz. That's fast enough. Well, pretty fast anyway. So sometimes we see things are not consistent. Here it says the ADC is not consistent because micros measurement is not that accurate. Remember, micros is giving us numbers that are plus or minus 4 microseconds. And so that's why we say it could be 8, it could be 4, it could be 12. You know, measuring micros is not the most accurate way to measure things if we want to get down to the microsecond, because he's only accurate to within 4 microseconds. So it looks like the A to Z converter is not consistent. It's not consistent. Look, we're getting different conversion times. What's going on? Well, the micros measurement is not that accurate. And that's just, I guess, a limitation of the micros measurement, put it that way. So that's what I have for you for today. I think we got through most of homework 6. Hope it wasn't too tedious for you. You guys didn't have any questions, but I think it was good we covered it, wasn't it?
Yeah, it was. Thank you.
I'm glad we did that, because I got a sense that maybe there was stuff in here you didn't know. And so that should help. And if you want, we can cover it a little bit more in our next exciting class. And we're going to have a lab, and I will be there in the lab physically. But meanwhile, we're going to stay doing distance learning lectures for now. Thanks a bunch. Stay safe, everyone.
Thank you.
Thank you.
Thank you.